All right, Liang Xiao will talk about p-adic functions on ZP, lecture 1. Take it away.
Okay, thank you very much. So everyone can see the screen, right? The screen I'm sharing.
Yep.
Okay, wonderful. Okay, great. So in these 4 lectures, what I want to do is I want to somehow introduce you to the so-called p-adic world and talk about sort of p-adic functions on ZP. But today, I'm just going to be very light, just talk about what p-adic numbers are and what's interesting about them, and there's some sort of interesting things you can do with them, and also talk a little bit about p-adic evaluation, p-adic norms. So maybe I'll just get started. So why do we study p-adic numbers? So this comes down to a very important philosophy in number theory. Is that in number theory we want to understand the rational numbers q or integers z. So usually, or at least classically, we know that we can take a completion of this q, then I get the real numbers. That's something we've all have seen. But for number theory, sometimes we want to understand sort of congruences modulo a prime or a power of primes. So that's going to lead up to something I'm going to call sort of p-adic numbers, in the sense that for each prime number p, could be 2 or 3 or 5, I can consider equally some sort of completions of the rational numbers q. And there are one for each prime number p. And our slogan is the following, or slogan for the number theorist, is that many theory that people have developed, many theories over R that people have developed, should have their analogs over QP. And they're equally important. For arithmetic applications. In the sense that many theorems you've seen or theories developed over R, you should do it over one of these things, Q1, Q2, or Q5, or whatever. And the many things you prove using analytic methods or real analysis method, or sort of number theory questions, there should be a way to do the same thing using these fields. So that's somehow sort of the general philosophy in number theory. And even better is that when you combine all of these information about each of the Q2, Q3, Q5 for all the primes, and together with the analysis sort of at R, at sort of the reals, and you can gain altogether some further information about Q and solve some much more difficult questions about rationals. But we won't get that far. So because I only have 4 lectures, so my goal will be concentrated in just introducing this QP, the Q5, Q2, Q3s. So here's the definition of ZP, or like this sort of the when you have sort of the integers inside Q, and therefore there's some sort of corresponding sort of integers in QP. So ZP is going to be inside QP. So the way I want to present it is going to take a analog to the reals. I want to think of how did we define real numbers at first place, right? Remember we learned when we construct these numbers, from the foundation of mathematics, we first constructed natural numbers and integers, and then rational numbers, and then we take some sort of completion to get R. But what really happens is that, for example, think about what happens. So I just randomly write down some sort of numbers, sort of infinite, digital numbers. So basically any infinite sequence like this with coefficients in zeros from 0 to 9. Oopsie. Give me a number basically between 0 and 1. And the way we do this is that somehow I read it. If you think about it, what really happens is that this is equal to 2 times 1/10 plus 7 times 10 to the negative 2 power, negative 2 power, and then plus 5 times 10 to the negative 3, and so on and so forth. The way you write down this this real number, which is not periodic, or just genuinely real number, not rational number, is that you just write down some sort of sequence like this. And what a p-adic number is, it's really just an analog of this, except now my p is going to be a prime number. For example, I just wrote down here 2, 3, 5, and 7, 11, and so on and so forth. And 2 plus 3p, I just write down similar things like what we did over here, except instead of having these sort of negative powers of 10, I just have positive powers of these. And I can put 0 if I want. I don't know what, 6, say. And go on. I can let it go on forever. So a p-adic integer is, just by definition, an infinite sum. Or more, maybe power series in the number p and with coefficients in 0, between 0 and p minus 1. Okay, so let me, before somehow trying to make sense of this, let me explain how to play with it. And once you're somehow, I guess my philosophy is that once you know how to play with this enough, you somehow start to accept that this is something that seems to be working. So I'm just gonna start with an example where p equals 5. As we did before, so I have some sort of a power series in the number 5. So what that is, let's say I took 2 plus, 2 plus 3 times 5 plus 4 times 5 squared plus, say, 5 fourth, and so on and so forth. And then I want to add another number which looks similar, of 2 plus 4 times 5 times whatever, and go on. And how do I add them together? Well, what I do is the following. So I look at sort of the first two terms, and just like how you add power series, you look at somehow the corresponding terms. So 2 plus 2 give me 4, so I write 4 here, and I keep going. So now I look at the next term, 3 times 5 and 4 times 5. So then I'm gonna get 7 times 5, but that doesn't quite work. Because we see that earlier, I said, okay, the coefficient must be between 0 and p minus 1, so therefore there can't be bigger than 4. So what I do? Well, I want to rewrite this a little bit. So I want to rewrite this small part. 7 times 5 as 2 plus 5 plus 5 squared. Because I break 7 into 2 plus 5. And therefore, now when I do the next calculation, so I can basically strike this out. I don't think of this. I think of 4 plus this and this. And when I do the square thing, maybe I should rewrite this a little bit. Or you know what? I just change this a little bit. If it doesn't work the same way I want it to be. So now I'm going to add these 3 together, because they are all sort of coefficients of 5 squared. What do I get? Well, I get something like 6 times 5 squared. Again, I'm going to strike it out and write, 5 squared plus 5 cubed. And the next thing, I'm going to sort of combine all the cube terms and then keep going. So this is sort of this thing continues. And the idea is that somehow you start with the lowest term here, 2 and 2, you get number, and then start with the numbers which somehow some multiples of 5. And each time if you get something a little bit bigger than 5, you break it up. You break it up into 2 times 5 and something a little bit higher power, and keep this going. Okay? And maybe if you want to compare this with the real world, it's a little different, I should say. I mean, because, well, what do you do?
Liang? I can't hear you right now. I lost you there. Let's see. Liang, we can't hear you. I can still see your screen. Some of the voice is gone. Hmm. Hello, Liang. Well, this is what happens. Technical problems. Maybe it looks like Liang might be coming back. Hi, Liang.
Albert, can you hear me now?
Yeah, I can hear you now.
Okay, good. Sorry about that.
Yeah,
I don't
that's
know.
okay.
Maybe somehow I can hear you when you ask me, but then I somehow it's just a question of upload. I'm very sorry about that. Can
Oh,
you?
that's okay. Since hopefully everyone is we're gonna have to be patient with the technology. So
Can you allow me to share my
I'm
screen?
sorry.
I think you
I'm
have to
sorry.
do something.
I thought you were still a presenter. There you go. Now
There we go. Because yeah. Anyways,
allowing you to present again.
let's see where I left. Hey, so everyone can. So where did I?
There you are.
Where did I lose everyone?
Oh.
I feel like not much. I feel like without
It was right when you wrote the green text.
Right. Okay. Sounds good. Okay. So we've done this calculation. So how I explained. So I explained okay the how to add two p-adic numbers just basically. So how add the first two and then so to multiple of 5 and then talk about those multiples of 5 squares. But of course there are some of the multiple of 5 squares coming from reorganizing this and basically you sweep these things to higher and higher powers of 5. And then okay, and then I want to look at sort of what happens on the reals. It's a little bit different if you think about it. For example, if you have if you want to add two numbers, you don't quite start from the left, in a sense because we have 7 plus 3, you get 0, but then you move, somehow you sweep things to the left. So it's a little bit different, I guess. But in some sense, in general, I guess these two are relatively similar in the sense that somehow think of this sort of this what's it called? These numbers adding together as sort of power series looks very much like what we do for p-adic numbers, except the p-adic numbers sweep to higher and higher power of p. Higher and higher powers of p. On the other hand, if we add real numbers, we sweep to the left somehow. And what about multiplication? So here's another example. Let's see. I want to multiply these two together. So what do I do? Well, so I have to maybe maybe here's a way to, I don't know whether I can present it well in this way. So basically you have to multiply all the terms together in some sense. Sorry, excuse me. So maybe it's better to do a table like that. It just, there's no good way, I guess. 2 times 2 is 2, and then over here you have 6.5, and then 2 times this is 8 times 5 squared, and over here you have 8 times 5, and then these two multiplied together, you get 12 times 5 squared, and this is 0, and so on and so forth. Okay? And then the next thing is I want to add everything, all these sort of many terms together. So the way I do that, I have 4 here, I just get to 4, and I have these two. That's going to give me, I guess, 14 times 5. So as I did for the addition, I want to rewrite this as 4 times 5 plus 10 times 5. So that's 2 times 5 squared. And next thing I want to have these two. I mean, this is 0, so I don't. And together with this, I will be altogether, I guess this is 22 times 5 squared. And I want to rewrite that as 2 times 5 squared plus 4 times 5 cubed. Remove that, and then keep going. And then, keep moving things over here to here and then add things together. So that's basically how you do multiplication of two sort of p-adic numbers. And so this is basically how you work with p-adic numbers. You can add them together. You basically add term-wise, and then whenever you see something which is a little bit bigger than p, and you sweep to higher and higher powers of p. It's okay, but it's a little awkward. But when you actually do the computation, it's not very convenient as you want it to be, I guess. So I want to present a slightly different point of view, which is a little bit better, I guess, in some sense, when you want to compute it with it. So here's another sort of equivalent definition, as we'll see in a bit. A p-adic integer is a collection of a1 mod p, a2 mod p squared, a3 mod p cubed, and so on and so forth. Well, before giving the conditions, maybe let me just sort of give an example of why this is the same as the powers that I wrote down earlier. Here's an example. There's a condition here, maybe I should say, such that there's a condition. But before giving the condition, let me sort of say how they are correspond. So if p equals 5, I have a 5-adic number. Let's write it down with this. To say this is sort of plus 4 times 5 squared plus so on and so forth. I want this to correspond to the following sequence of. I want from this number to get a sequence of mod powers of p's. So what I do is I want to replace this by 2 mod 5. And if you look at this somehow, what is the mod 25? Well, the only thing that matters is the first 2 terms. So that's 17 mod 5 squared. And the next thing is somehow the first 3 terms. So that's looks like 117 mod 25. Right. So basically, from a power series I had earlier, I get a sort of mod p, so mod 5 squared, and mod 5 cubed, which is 125 if you want to know. Okay. But I can write down random sort of congruences, random these things. So there's a condition you have to satisfy. That is a n plus 1 congruent to a n modulo p to the n. So these must congruent. For example, 117 is congruent to 117 modulo 5 squared. So I just want to make sure that I'm not lost. I'm not losing you.
I'm good. Okay,
You're sounds good. Yeah, I probably opened too many sort of like videos and all. I have 2 computers running at the same time, and so anyways, sorry about that. Okay, so how do we think of addition from this point of view? Well, if I have a collection of say an mod pn, and I want to add with another collection bn mod p to the n, I'm just going to say so this is collection. So each one of them has a1 mod p and a2 mod p squared and so on and so forth. And I want to say the addition will just give me an plus bn mod p to the n. So that looks really simple. But what's I mean, but why was it so difficult for the other power series to compute the power series addition? Well, let's do an example of how this is done, the addition. So remember, I have a power series like this, and have another sort of power series expression of this p-adic number. So how does it correspond? So the first one corresponds to 2 mod 5, comma, I guess 17 mod 25, and this is a 117 mod. I should just copy things from 125, and so on and so forth. And this one is 2 mod 5, 22 mod 5, 25, excuse me. And then this is sort of 47 mod 120. And then when I really add them up, I get 4 mod 5. And this will give me 39 mod 5, right? Just add the two numbers up. And this is 162 mod 25. And if you think about this, I mean, of course, 39 mod 25 is okay. It's something that makes sense. But I rather, like to write it as 14 mod 25. That looks, normal to me. Even the thing in front of mod 25 should be somewhere between 0 and 24. And similarly, this one should be actually congruent to, or rather, sort of when I mod 25, the same as 39 mod 125. And somehow, if you think about what really happens, zoom in a little bit. So when I do this addition earlier on, I have a lot of replacing the 7 times 5 by 2 plus 5 and 5 squared, and over here I have some sort of replacement here. That's basically essentially what happens here. I replace 39 by this 14, and then this 162 by this 39. So that's somehow, I guess the two computations are essentially the same in the sense that over here I express things in terms of sort of power series, in some quotation power series in 5, and over here I somehow have to modify these sort of modulo higher power p into their sort of primitive forms. So this is somehow where the sweeping happening. Okay. Right. So this is basically kind of a quick introduction of how p-adic numbers is and how it works. So now I'm gonna come to the next sort of cool thing about p-adic numbers is that we can do a lot more things we can't do over Z. Here's the theorem. If A is an integer that is relatively prime to P, then A is invertible in ZP. Or here's an example, maybe if P equals 7, then what I'm saying is that this, if I write this, for example, 10 times x equals 1 can be solved. Well, we know it can be solved over Q, but it actually can be solved in Z7. You don't have to go to the rational numbers. You just, in the sort of 7 adic integers, you just solve it. Of course, I'm not gonna prove this. I'm gonna prove something even cooler than this, and somehow the method will be exactly the same. So here's another example, which I'm gonna actually run a similar argument. So you're gonna take p equals 7. What I want to do, I want to really solve x squared equals 2 in Z7. Namely, somehow we know this x must be root of 2, but somehow root of 2 has its avatar in some sense in Z7. So root of 2 is already in Z7. So let's do this. So step 1. So remember what is really Z7 here? We said that, oh, I didn't really define Z7. Shoot. I mean, I'm very sorry about this. So what ZP is all the p-adic numbers, p-adic integers. Excuse me. What is this? Okay. So I'm going to use the second point of view. A p-adic integer is just basically a collection of these higher powers of p. So if I want to determine a x, if I want to determine an x that squares 2, I better first of all determine what this x is modulo p is, and what this sort of the modulo p square is and modulo p cube is. So that determines my steps. So my first step is to solve x squared congruent to 2 modulo 7. And that's something we get, I guess we can sort of do by hand, checking all the possible sort of residuals mod 7. So we see that x could be either congruent to 3 or congruent to 4 mod 7. And for the later steps, I'm going to fix one of them. Oopsie. I want to fix one. This one for the rest of our discussion. Okay, step 2 is that once we've done that, I want to solve x squared congruent to 2 mod 49, which is square root of 7. Of course, I can go through all the residuals of mod 49, but that's going to be a little bit take some time. But here's something. I already know that x is congruent to 3 mod 7, so I can take advantage of that. Namely, I know my x must be equal to 3 plus 7 times a, because it's congruent to 3 mod 7. So now I want to plug in this x equals 3 plus 7a into the equation I want to solve. So this was, let's expand it out. So mod 49, 49a squared disappeared. So now I have 7 plus 42a is congruent to 0 mod 49. Now I want to divide by 7. I'll get 1 plus 6a congruent to 0 mod. So when you have a congruence, congruence relation, we'll divide everything by a number, say 7. What end up getting is that you only get mod 7, not mod 49 anymore. So this will tell you that a is congruent to 1 mod 7. So let's go back to this x equals 3 plus 7a. So x is congruent to 10 mod 49. Hooray, I solved this. Now the next step. You kind of know already what I'm going to do. I'm going to just, again, solve x squared congruent to 2 mod 7 cubed. Oh, this is 343 if you want to know. I don't think it matters. I want to write x equals 10 plus 49b. Because I already know that x is congruent to 10 modulus 49. So again, I do the same thing. Congruent to mod 7 cubed, maybe. This is it's going to be complicated. Plus 49b squared congruent to 2. But then you see again mod 7 cubed. But this will go away. 7 fourth power, even higher power. And then now you have this mod cubed, and then you divide by the same thing, and then you divide by 49, and then solve for b, and then bring it back, and then continue this way. Basically, the upshot at each time, if you think about what happens, is that over here, you always have something looks like something with a 7. So this is 7 squared times something, and this is sort of 7 times 7. And if you divide by 7 squared something, you can always solve for the b. And if you continue this way, you will get what x is in Z7. So indeed, you can really solve x squared, or find root of 2 in Z7. So in fact, so maybe I should sort of stop here and wait for if there's any questions, and also in case I lost myself again. So Albert,
I can hear you. It's been fine. So yeah,
sounds good.
If anyone has a question, let me know. Raise your hand. I can give you the. There you go. Hi, Owen.
Hello.
Hello?
My only question is, I think that last equation has no solutions.
The last equation. Oh, sorry. Yes. Right. Better?
98 plus 98b squared equals 0 mod 7 cubed. I don't think that has any solutions.
You don't think this has a solution? Well, let's see. I mean, like divide by 48, 9. You get 2 plus what? 20b. Right?
Oh, 980. I thought that was just 98.
Yeah, I can't-
well,
I
like,
can't
98,
read.
Sorry,
Thank you.
I did something wrong because when I get, sorry, I did some calculation. But even 98, right? Even 98, I still got 2 plus 2b equal to 0. So b is 6. But right
B
now, I guess
squared.
the correct one b is 2.
No, it'll be b squared. I thought b squared would have to be 6 mod 7.
Oh, my bad. Sorry. I'm sorry.
Anyway, you fixed it. I was
I can't
looking
do
at.
square. Sorry.
I was looking at
That was my
previous
bad.
version, as I always seem to do in life. Thank you.
I apologize.
Thank you, Owen.
Thank you.
Let me
Questions? Sorry.
yeah, let me see if I can somehow Diwang would like to oh, there is a Diwang has a question, but somehow your audio panel is not working, Diwang. Oh, there you go. Diwang, do you have a question?
Hear me?
Yeah, I can hear you now.
We can hear you now.
Yeah, I was just going to ask, is the multiplication like pointwise as well once we view this in the sequence format?
Sorry, I didn't quite get it. Could you
Sorry,
repeat your question?
Yeah, like when we switch to the sequence format of p-adic numbers, the addition becomes pointwise. Is the multiplication the same way?
Yes.
Okay, just wanted to clarify.
I should have said that.
Okay.
Yeah, right. Oh,
Yeah.
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 Is there space? I can. For an extremely lazy person, I'm going to do this. Let's see. Ugh. Right, so what I'm going to do is, there we go. Okay.
Thanks. Yeah.
Okay, thank you for the question. Sorry.
Yeah.
Yeah. So multiplication is the same way. That's right.
Very good.
Okay.
Somebody else had a question? I think there was a third hand. All right. Well, if not,
So continue then.
yeah, continue. Thank you.
So continue. So now I'm going to talk about the vast generalization of what the method I just talked about, without giving the proof, unfortunately. But Hensel's lemma is the following. So if I have a, say, x to the n plus, more general, a monic. So this is important. This is a monic with its coefficient z, and assume that I have fx if I modulo p. So all the coefficient modulo p. So that's going to be in a polynomial in fp. This has a simple zero alpha in fp, also in fp. So namely, if you can somehow factor this polynomial fp with coefficient fp into somehow factors, there's this x minus alpha only appears once. Then there exists a unique zero, call it alpha tilde of fx. Maybe I just write it here. Alpha in zp of fx, such that this alpha tilde modulo p is my alpha started with. So basically, the point is, if you have a simple zero, or put another way, if you have a simple zero, you can lift it uniquely to a zero of fx, and then its reduction is just what you started with. Just to give you a sense of what, like in our earlier example, what it says is if I apply this to this case, fx equals x squared minus 2, and I try to solve this, it, and somehow if you know that fx, if I modulo 7, this has two zeros, namely 3 and 4. They're simple zeros, of course. And I take my alpha to be 3. And then the Hensel's lemma basically says that I can lift to a alpha tutor such that alpha tutor square is 2, namely it's a solution to this one. And also alpha tutor, if I modulo p, gives back my alpha. And somehow the proof of this more general Hensel's lemma, or more difficult sort of polynomials, works exactly the same way as I just explained. You just first of all mod p already gives you, right? Then you do mod p squared. Each time, basically, you observe that the thing you want to somehow invert. For example, over here, you want to solve this from 1 plus 6a coming to 0. The 6 is always not 7, basically. Something you can always invert. And over here, you have some sort of, even if you have 980, and then when you divide by 49, you get down to something like this, where this 20 is invertible. So that's basically the essential idea of this. And what that is so what makes that work is the simple zero of that condition over here. So due to time, I'm not going to give I'm not going to explain the proof of this, but I want to explain how to use it to do something really interesting, I guess, or sort of very useful later on. And also this will be useful in, I guess, Keith's course later on. So I want to consider a very special equation. Mod p, what's happening? Well, if you look at this equation mod p, so it precisely has p minus 1 zeros. Namely, there is not. 1 through p minus 1. And why is that? Well, there are two proofs. First of all, this is a Fermat's small theorem. I think it's called Fermat's little theorem. Not the famous one, unfortunately. Well, another way to see it is if you look at Z mod PZ cross, and this group has order p minus 1, and you use Lagrange theorem. And every element in here, if you multiply it p minus 1 times, it gets to the unit, which is 1 in Z mod PC cross. There are two ways to see it. But anyhow, this degree p minus 1 polynomial has exactly p minus 1 0, and they're different. So every single one of them is a single 0. Now I can apply my Hensel's lemma to my fx. You see that all I want is that the mod p, I have simple 0. I can apply to each one of the simple zeros I have at hand. So by Hensel's lemma, for each a in this list, there's a unique called a tilde. Oh, excuse me. Let me not call it. Let me call it bracket a. This is somehow the standard way to write this in ZP, such that first of all, this bracket of a is common to a mod p, and secondly, this bracket a to the p minus first power, because the solution to this equation is actually literally equal to 1. In other words, so this will tell you that this bracket a is a p minus first root of unity, i.e. This ZP contains all p minus first root of unity. And also they do form a group in some sense. So therefore you see that AB is equal to A times B, in the sense that you see that, I guess you see that if you do I guess maybe write it down here. So because you see that, because if I do A times B, altogether P minus first power, that's the same as this to the P's power, and that's just 1. So in other words, this A bracket or A bracket times B bracket is a solution to my equation. And on the other hand, this is also congruent to AB mod P. And by the uniqueness of the lift, they must be equal. So that's that's somehow how you find root of unities that's congruent to your given residual modulo P. Sorry. Another thing is that there's a name for this. Why I somehow pick this particular weird notation. This is called a Teichmuller lift. Lift of A. This will come out later. So let's make it a little bit explicit. So what Hensel lemma does is really, in some sense, somehow solving. what Hensel lemma really says is basically you just solve this equation mod higher and higher powers of P. So here's an example. So if P equals 7, and you're trying to really somehow solve these equations. So let's say you want to solve this modulo 7 cubed. So, so you can start with sort of x congruent to one of each of the sort of 1, 2, 3, 4, 5, 6. And so here's the answer I give you. So of course, 1 always lifts to, oopsie. So 1 always lifts to 1, and then 2 will lift to this thing. And then if you want higher precisions, you have to go on to add something 7 cubed, and then so on and so forth. And then 3 is this, and then so on and so forth. And maybe I just point out one thing. The last one, this is -1 in disguised form. So basically what this thing should be is plus 6 times 7 cubed, and then 6 times 7, and so on and so forth. And those 6, 6, 6, 6, 6, 6, this is sort of -1, really. Right. So let's see how much I have. So Elroy, can I take another 5 or maybe, I guess probably 5 minutes won't do it. Probably like almost close to 10 minutes.
Sure, about
Well,
5.
I'll try to minimize this.
Let's try to give it to 5 or so, but since you lost a bunch of time, let's just say 10 minutes. Let's say until 11.
I think I'll try my best to finish as soon as possible. Or maybe I should stop here slightly and then wait for some questions if there's any. About the Hensel lemma, it's a very important lemma in p-adic numbers. So allows you to solve, I guess, very different from integers in the sense that in the integer world, it's really difficult to solve an equation like this. But in the p-adic, all you need to do is solve the mod p, and somehow, almost always, if you as long as you get simple 0, it gets lifted all the way to zp. So that's the nice thing about this. Are there any questions about these? Okay, so maybe I'll move on.
There's one question, Liang.
Oh, there's one question. Yeah, go ahead.
Would you, I think the person asking the question, Kirk, you would have to fix your audio panel, start.
Or maybe you can, okay. Or maybe you can rephrase the question.
Oh, there you go. Hi, Kirk.
Right. So earlier you spoke about condition for the p-adic integers where you have an plus 1 is congruent to an.
Yes.
An. I'm not sure if I fully understand that. In this latest example, I'm not sure how that lines up.
How that interplays here. I mean, like if you think about this, so what that comes into place right here. So the first one you solve for x comes to 3, and the next one you want to solve it for something modulo p squared, but then you want it to be compatible with this a1 mod p, right? Right? You want it to be compatible with this. So that's why you have to say x is 3 plus 7a, so that this new x, namely your a2, is congruent to your original a1 mod this. No,
Yeah,
on
I
this
see
step,
that
A3 mod.
in this example. I see that in this example. So I was looking at the one.
Does that answer your question?
You hear me?
Yeah,
I
yeah,
can
you were
hear
going
you.
in and out, but yeah, we can hear you, Kirk.
Yeah, I was referencing the last example. The numbers you wrote there.
Yes.
Yeah, they didn't seem to line up with those congruences, so I was confused. Exactly.
X equals 10 is congruent to 3. Oh, maybe you want to ask about what happened to 4?
No,
In order
I'm
to do 4, you have to start with a different one.
talking about the one at the bottom of your notes.
Yes.
This one, these numbers, are these supposed to be under those same constraints?
No. I mean to say that. I mean, I guess I'm. So I mean that for each 1, 2, 3, p minus 1, you have a way to lift it to a p minus first root of unity. So 1 will be lifted to 1. 2 will be lifted to this number. Plus, I mean, supposedly plus something. 7q plus all the way.
Right.
And each one of these are not related.
Okay.
Because they come from different root in some sense. You should think of these sort of mod p solution. They are kind of a root of your way to solve things.
Right. The coefficients of like for 2, like 6 isn't congruent to 4 mod 7. That's what I'm confused about.
They don't have to be the same. I mean, basically, what this thing in terms of modular, this is 2 mod 7, and then this is I guess 30 mod 7 squared, and then add this. I don't know what it is. I mean, like 49.
Yeah.
I don't know what it is. Sort of 3 something mod 7 cubed. I don't know. I have to compute, but yeah. So that's what it looks like.
I see.
Sequences.
I think I just have to spend some more time thinking about that.
Okay, so that answers the question.
Thank you.
Thank you, Kirk.
Okay, so let's move on.
Liang, if you want to continue, and then we'll take questions at the end.
Yeah, that's what I'm doing. So okay, so now I want to talk about the third way to think about this in the last 5 minutes, but hopefully this should be enough. This is the limit. When I think about the real numbers, this is the limit of a bunch of numbers. I mean, x1.2 and then x2.2. You know, and of course, what this thing, you want this to be goes to 0 as n and m go to infinity, right? So that you form kind of a Cauchy sequence. And I want to do the same thing for the p-adics. So I think, for example, I think of this as limit of, I guess, x1 equals 2, x2 equals 2 plus 3p, and x3 equals to, you know, the first 3 terms and so on and so forth. And again, I want to, and what happens here is that somehow this xn minus xmn is a higher, or what you see in terms of property is divisible by higher and higher powers of p. So here's a definition. So I want to make sense of this. Somehow I have to relate higher and higher of p with sort of this distance being going to 0. So that's exactly what I'm going to do. This is what happened for the p-adic world. So to fix p a prime. So a so-called p-adic valuation of an integer n is, so denoted by vp of n is I guess the largest integer such that p to that power divide n. I think there's a notation. I'm not sure if everyone has seen it. People usually write double dividing n means exactly divide n. Here's an example. Here's an example. P equals 5. So the 5-adic version of 3 is just 0. But if you take 5-adic evaluation of 75, that's divided by 5 twice, so 2. Okay, and what about 0? 0 is considered infinity evaluation because it can be divided by p as many times you want it to be. And the p-adic norm is different from the usual absolute value of n. I'm gonna write looks like absolute value, but I want to put a lowercase p to indicate that we're talking about p-adic things. This is p to the negative power of this. So what happens is that, but I want to somehow in the p-adic world this works at the same way as the absolute value. But I want to put the subscript p to distinguish from this this usual absolute value. So, for example, if I do 3, the 5-adic norm of this is just 1 because 3 is not divided by 5. Whereas if I do 75, as an example over here, so the 5-adic norm is 1/25, it's 0.04. It's very, very small. If I do sort of, for example, 5 to the 12 times 7 times 11, whatever, that's just 1/5/12. So these sort of factors will not matter. So the slogan here is that more divisible the number is, the smaller its p-adic norm is. So you see here you have to divide 5 12 times, but the norm is 1/5 to the 12th. So the p-adic norm, the big theorem is that the p-adic norm defines a metric space structure on Z. That's to say that for x and y in Z, I can define their p-adic distance. Maybe I'll just d sub p x y to be their difference, and then take the p-adic norm. And then ZP is a completion of this. With respect to this, maybe with respect to this distance dp. Let me go back to this example earlier here. You see that somehow we started with this 2, and then I add 3p to that, and I, think of it as sort of a point on the space, right? I start with 2, and then I change it by 3p, and then I change it by 4p squared. But somehow in terms of distance, p-adic distance, what I did was that, so this has whatever distance 1 to 0, say. And the next time when you move by 3p, you move this distance, p-adic distance, by 1/p. It's not too much. And next time, the next time when you move it by 1/p squared. You move it even smaller. So as you somehow go down this list, you move it smaller, 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 and this does become a Cauchy sequence with respect to this p-adic metric. Okay, so let me sort of quickly say that this theorem needs a little bit of proof. I'll do that next time. And also next time I'll give you a picture of ZP, of what it looks like, because this looks a little bit weird. It's somehow one of the maybe distinguished thing is that somehow anything you can write in ZP, if you take the p-adic absolute value or p-adic norm, it's always less than or equal to 1, because you see all the numbers here are less than or equal to 1. So therefore ZP is all bounded. This is very different from, or maybe Z is all bounded. Maybe just excuse me. Okay, what I wrote was okay. Z is bounded in p-adic norm. In p-adic, excuse me. But of course, not bounded in our absolute value, usual absolute value. So therefore, the intuition is not quite the same. So next time, I guess tomorrow, I'll talk about this. And also, there's no order in ZP. On Z, you can A bigger than P, A bigger than P, excuse me, A bigger than B or something. On ZP, there's no inequality. Okay, sorry for running over time and then the interruption of internet. I'll stop here.